have a class addressing models. Addressing models. When we make a program, we need to know the address and how to access the address. So I introduce the addressing model. The CPU can access data in various ways, which are called addressing models. Immediately register, direct, register, indirect, and indexed. 1, 2, 3, 4, 5. 5 addressing models. Direct and indirect indexed is for accessing memory. Accessing memory is for RAM. ROM is okay. Immediately address model. The source operand is a constant. The immediate date must be preceded by the pound sign. If you see the pound sign, you know it's immediate model. Can load information into any register, including 16-bit DPTR register. DPTR can also be accessed as 28 bits, which means DPTR data point has 16 bits. We can access high bits and no bits. High 8 bits, no 8 bits DPTR. For example, here is an example. This is move A. You know move A, pound 25H. Move R4, pound 62. This is just a move. You can see move DPTR 6 bits. Here is DPTR 8 bits. If you move DPTR pound this number is wrong. Which the maximum numbers is 4F, 4FH. 65,535 is the maximum number. So if you bigger than this number is illegal. We can use EQU directive to access immediate number. For example, count EQU 30, 30, which means count represents 30. So if you cannot understand the program, you can replace count with 30. Move R4, pound count. You can replace the count with 30. move dptr pound my data, which means my data is a label, but it's a label address. You can replace my data with my data's address. My data address is 200h. So this example, you can replace the count with 30, my date with 200, 200h. We can also use immediately address model to send data to 51 port. This is right. This is right. Move P1, pound 55H. Register address model. Use register to hold the date to be manipulated. Move A, R0. Copy contents of R0 into A. Move R2, A. Copy content of A to R2. Add content of R5 to A. Let's use the register R. Hold the date. Register R to hold the date. The source and the destination registers must match in size. If you do the exercise, move dptr, A will give an error. A is 8 bit. dptr is 16 bit. For example, dptr has 16 bits. If you store the dptr into R register, you need to separate dptr two parts. This means dpl and dph. The movement of date between R and registers is unknown, which means you cannot use move R, R is invalid. It is most often used direct address model to access RAM location 30 to 7FH, location 30 to 7H. The entire 128 bytes of RAM can be accessed. The register bank location are accessed by the register names. Move A, 4 and move A R4 is the same. Which means copy R4 into A. Contrast this with immediately address model. If you use the immediate address model, there is a pound. Before the immediate number. The SFR can be accessed by their names or by their address. Name or address. If you use the name and use the address, it's the same. The SFR register have address between H0H and FH. Not all address space of H0 to FF is used by SFR. The unused location of location H0H to FH are received but must not be used by the AV41 program member, which means the memory space between H0 to FF is not used or by the user. Here is the name and the address. Here is the name and address in the SFR registers. You need just remember the symbol. You need the symbol, and when you program, you just use the symbol represent the address. But if you can remember the address, is better. Here is the example. Red code send FFH to port 1 and port 2 using their names or their addresses. Use the name P1, P2, P1, P2. Use the address H0H, A0H. This program and this program is the same. The stack and direct address model. Only direct address model is allowed for pushing or popping the stack. Direct address model. Push A is invalid. Pushing the accumulate onto the stack must be coded as push 0 E0H. You cannot use push A, but you can use push 0E0H. Show the code to push R5 and A onto the stack, and then pop them back into R2 and B, where B equal to A and R2 equal to R5. Pushing 05, push 0E0H, pop 0. This one equal to this one. This one equal to this one. This one. A register is used as a point to the date. Only register R0 and R1 are used for this purpose. R2 to R7 cannot be used to hold the address of an operand located in the RAM. So we remember R0 and R1 are used for address point. Point to the date, point to it. It means the address point. When R0 and R1 hold address of RAM location, they must be preceded by the H sign. If you know something about the C language, you know H sign is for address, the address. Move A, HR0, move content of RA whose address is held by R0 into A, which means not copy the content is R0, is the content of the R0 address point to content. So the H sign for a special purpose. Move H R1, comma B, move content of B into RAM, whose address is held by R1. Whose R1? Yes, address is stored in R1, not the content. Here is an example. Write a program to copy the value 55H into RAM memory locations 40H to 41H using direct address model. Reduce the indirect address model without a loop and with a loop. This is three solution. Move just use move directive. Just use move directive. Copy the value 55 to RAM memory 40H to 41H. Use direct address model. Solution B is register indirect address model.
Is that a mistake? Move 41H and solution A.
You mean here?
Yeah.
Here.
No. Yeah.
Here. Here. It's a comma.
Yeah.
It's a comma. Yeah. Sorry. When we exercise something, do some exercise according to the PPT, if you found some error, you need correct it. Yeah. Last time I saw your assignment. You just do one exercise.
We recorded one exercise.
You exercise all the example.
Not all, but
Not all. Just some. Yeah.
Just one love see. We can do. That's right.
You can do as example.
It's now we can do because we know.
Okay.
That's the reason one is okay.
Yeah. Okay.
But just we take some program and we can do it right or wrong. Okay.
Yeah. I mean, if you don't understand the address model, just here I told you, you can run the program in the Protos, so you know the address relation between the code and the directive.
We can also use this tree program, right?
You use this?
This we can use
Yeah.
this tree solutions 1, 2, 3.
Uh,
ABC.
You mean solution ABC? You can use run the program in the Protos. Yeah. If you do something by yourself, you know the actually meaning of the directive. So you know the meaning of the directive. So I don't introduce just the directive. If you have some time, you need to do some exercise with Protos. Okay. Register indirect addressing model. The advantage is that it makes accessing data dynamic rather than static as in direct addressing model. Which means you can change the content of register. Looping is not possible in direct addressing model. So if you want to use loop in your program, you cannot use immediately address model or direct address model. So you need to use register indirect. For example, write a program to clear 16 RAM locations starting at RAM address 60H. Here is the solution. CLA A equal to 0. Move R1 pound 60H. Note point R1 equal to 60H. The RAM address, first RAM address. Move R7 compound 16, which means there are 16 address. 16 address you need clear. This is a loop. Again, move 8 R1, A. Clear RAM R1 point 2. It means clear the content of R1 address. INC R1 increment R1 point. R1 point which means R1 address. DJNZ, which means R7 decremented by 1 until until 0, So if not 0, we can loop here. If R7 is equal to 0, the loop is ended. So this is register in indirect address model. Another example. Write a program to copy a block of 10 bytes of dates from 35H to 60H. Copy the start address. This is the destination address. Which means point. R3 is a count. R3 is a count. So here is a loop. Move A, H R0, which means the content R0.2. Get a byte from source. R0 in here. Move HR1, A, copied to destination. Is copied A to the address pointed to by R1 address. INC R0, INC R2, DJNZ R3, which means the count to 0 stops the loop. R0 and R1 are the only register that can be used for points in register indirect address model. Since R0 and R1 are 8-bit wide, their use is limited to access any information in the internal RAM. Whether accessing external connected RAM or on-chip ROM, we need a 6-bit pointer. In such case, the DPTR register is used. DPTR is a 16-bit register. R0 and R1 are 8 bits. 8-bit register. So if your address is more than 8 bits, so you need the DPTR register. Index address model is widely used in accessing data elements of lookup table entries located in the program ROM. An instruction used for the purpose is move C. A, H A plus DPTR. Use the instruction move C. C means the code. ROM. The content of A are added to the 16-bit register DPTR to form the 6-bit address of the needed bit. Which means your dates between the group of plus A or minus A. You can add your address to the DPTR and get your actual address. Accessing memory. Indexed addressing model. So you can use indexed addressing model. Move. This gets the DPTR. Start address. This is look up the table. Look up the table. A is equal to 0, which means the first number in your table. Here DPTR 200H. This is the table. So clear A is equal to 0. So move C A, H A plus DPTR. This means because A is equal to 0, so this is the first number of the table. Save the A to R0. INC DPTR, which means DPTR add 1, incremented by 1. So this is get the second number in your table.
Please. On clear A, the second line. Clear A. A is equal to 0.
Yeah, A is equal to 0.
The next line is A is equal to 55.
A is equal to 55. You mean here clear A?
Yeah, that is 0 here.
Yeah, A is 0.
Yeah. The
next here.
Yeah. A is equal to how much?
A is 0, which means this SA is 0.
Yeah.
So this represents the first number of the table.
Okay.
So move the first number of the table to A, so A is changed. Here A is changed. Yeah. So A is got U. U. Okay. If you use some person with this example, I introduce.
My problem is on this side.
Which here?
On the top.
Okay. Oh, you know why? You want to why? Okay. This is the program about move the word USA. Move the word USA in ASCII code. You know ASCII code, ASCII code. U is 55H. U is 55H. S is 53H. A is 41H. So here define a table. So there is three numbers in your table. USA. U means 55H, S 53H, A 41H, A41H. So we can see the program ORG00, which means this main program start from 0. ORG20H, which means the table start from 200H. So 200H. The first line gets the address of the table. Clear A, which means A is equal to 0. Move C, A, H, A plus dptr, which means A is equal to 0. So this just gets the dptr 200H. Here represent the address of the table. So move C just gets the first number of the table to the A. So you get A is equal to 55H. 55H is U. Is ASCII code of the U. So move A to R0, which means R0 is equal to 55H. So in INC dptr, just add 1 to the dptr. So we can the dptr point to the second number in the table. Clear A this gets the second number, gets the address of the second number. So move the second number to A, so we can get A is equal to 53H. Move R1, A, which means copy A to R1. INC dptr, which means here add 1, which means dptr is pointing to the set number. Clear A, which means get the set number of the table. So move to A. A is equal to 41H. Copy A to R2. Just wait here. And I will give you a task after we finish this PPT. You need to run this example for yourself. Run this program for yourself. Lookup table allows access to elements of a frequently used table with minimum operation. Lookup operation is used frequently because this code is executed faster. So there is there is some calculation in your program, but and the result you can make a table and look up the table, just get your result, not use the number to calculate computer. For example, write a program to get the x value from P1 and send x square to P2, Solution. ORG 0, start your program from 0. This is get the address of the table. Address of the table. Move A, comma pound 0 FFH. A is equal to FFH. Move P1, comma A. Configure P1 input port with P1 input model. Move A, comma P1. Get the x, get the number in the P1. Get the number in P1. Get x square from the table. This is look up the table. You can see the table. First is 0. The square of 0 is 0. Second is 1. So in the this is 0, 1, 2, 3, 4, 5. You know, in the computer we started from 0. So first one is 0. First one is 0. Second one is 1. So the square of 0 is 0. The square of 1 is 1. The square of 2 is 4. So 0's square is related to the address. You can use the table. Get the square and send the square to P2. Send the square to P2. Just loop here. In many applications, the size of program code does not leave any room to share the 64K byte code code space with date. The 8051 has another 64K bytes of memory space set aside exclusively for data storage. This data memory space is referred to as external memory. It is accessed only by the MOVEX instruction. So if you want to access external memory, you need to use MOVEX instruction. The 8051 has a total of 128 key bytes of memory space. 64 key bytes of code and 64 key bytes of date. The date space cannot be shared between the code and the date. Cannot be shared between the code and the date. In many applications, we use the RAM location 3027FH as scratch pad. So which means you can use it freely. You can use it freely. We use R0 to R1, R7 of bank 0 leave the address 08 to 1F for stack use. Which means if you reset your microcontroller or power on your controller, we can use bank 0. We use bank 0, but the bank 01 to bank R1 to R3, we leave for the stack. If we need more register, we simply use RAM location 30 to 7FH. Yeah, here is a map about your memory. You can see here is for the bank 0 when you power on your microcontroller. So here is bank 1 to bank 3. We need for stack. If you need more register, you can use general purpose memory, or just use here. Bit addressable location. If we need more register, we simply use RAM location 3027F. 3027F is 2F. Here is 30. Use the general purpose RAM as your register. Here is an example. We write a program to toggle P1 a total of 200 times. Use RAM location 32H to hold your count value instead of register R0 to R7. Here is your solution. Move P1. P1 is equal to 55H. 32H is storage. Save the 200. Here 32H. Here 32H is in the group 3027F. Note that 200 to 32H. CPL toggled P1. Echo delay. Just delay. DJNZ. Degree 32H by 1 until the content in the 3 to H becomes 0 until it becomes 0. Okay, you have a rest. You can rest. For example, here is a program. You can see the PPT. When I make the PPT, I write move P1 pound 55H. But if you use this code, CPLP1 is error. This book I copy to you. This book. This book I copy to you. Yeah, you can check the code on this book.
In this book, there are a lot of code.
Yeah, there are a lot of book.
A lot of code in this book.
Yeah.
You can practice, right?
Yeah, you can check that CPLA. It's a address model. Address model. Only A. Only A. You mean you can use this CPL with A, not other register, not other registers. So sometimes maybe if we forgot this one, we need to check the book. Check the book. So this book is useful for you to use the 8041. 8041. For this program, if I want to run in this program, you can see there is a core. A core means called subprogram. So called the delay. There is no delay. There's no delay. So need write by yourself or find from other PPT. Other PPT. If you need to be careful. Put the subprogram in the right position. If you put it in the wrong position, you will get some error. I can show you. I can start the start this program. Make a new project. next, 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 next. Just the empty project. You can pick the some file. Okay. Rather you code here. Rather you code here. For example, this program, this is the program I need to run. Yeah, it's the here. It's the here. Let's see, yeah. Just put here. And save the program. Save the program and build the project. You can find some error. One error detected on one of 38.9. You can check 38.9. You can check 38.9. A core delay DJZ is on the same line. You can separate two lines. Yeah, yes. Check here. Build again. Symbol not defined. 38 here. It mean delay not defined. So you need to write a delay program or find from the PPT. Just like here. This is PPT. I copy from the PPT. If you find put here, if you put here, there are some maybe some error. We can check. We can check. Put here. Build. Yeah, complying successful. We can try this. Start. Debug. Register. Debug. Internal memory. Internal memory. Debug internal memory. Yeah, you can see here. Yeah. Yeah, you can see here. But I changed the position of the code. Stop. You can hear is a loop, jump loop. If I put the code here, build, yeah, compile is successful. Start. I just run it and pause. You can see the program go to the that loop, Yeah, this is that loop. Just the loop itself, and loop itself. But if I put here, will not go to the that loop. So you can just exercise like me showing you, so know how to find your program, find your error and correct your error. So it's a process you must get through. You must get through the process. So if you understand the process, you mean get high level about the program. Yeah. So next time, I hope you can running every program on the PPT, and especially when you found some error, you can record the process you correct the error. Yeah, that's important. That's important.
Okay, so we will do no problem.
No problem.
No problem. We will do. No problem.
Okay.
It's in our book. Lots of example in our book.
Yeah.
That we use as.
You can use this book as your reference book.
Yes.
Yeah.
We have this book. We will try to practice.
Okay, let's continue the class, okay? Now, here is an error. We need to correct it. Many microprocessors allow program to access register and the I/O port in byte size only. However, in many applications, we need to check single bits, and byte size is different access model. One unique and powerful feature of 8041 is single bit operation. Single bit instruction allows the program to set, clear, move, and complement individual bits of a port, memory, or register. It is registers and RAM and I/O ports that need to be bit addressable. ROM are holding program code for execution. It is not bit addressable. Let's be careful. ROM is not for bit addressable. Normally we use RAM as bit addressable. The bit addressable RAM location are 20H to 2FH. These are 16 bytes, provide 128 bits of RAM bit addressability, since 16 times 8 is equal to 128. 0 to 127 or 0 to 7FH. Maybe we can check this table. You can find the table on your PPT or your reference book. This is the bit addressable location here from 0H to 2FH 20H to 2FH 20H to 2F 20 to 2F has FH bytes, which means in decimal is 16 bytes 16 bytes. The first byte of internal RAM location 20H has a bit address 0 to 7H 0 to 7H. You can see 0 to 7, 0 to 7. Here is 4 20H. Here is byte address. Here is byte address. Here is byte address. Here is bit address. Bit address. Different address. Normally we use byte address for the register, but sometimes if we need the bit, access the bit, we use the bit address. Internal RAM location 20 to 2FH are both byte addressable and bit addressable. Byte addressable and bit addressable. This byte address is bit address. So they direct to the same location. Maybe they can direct to the point to the same location. Just for example, this is a byte address 29H. If you use 29 for the 8 bit, but if you want to access 1 bit, for example, for A, you can use for A for the bit address, or use 29H point 012 point 2 for the 4A for the 4A. Bit address 00 to 7F belongs to RAM byte address 20 to 2FH. Bit address 80 to F7H belongs to SFR P0, P1, etc. This is a map about the memory. This is the memory. This is the example. Find out which by each of the following bits belongs. Give the address of the RAM byte in hex. For example, set B 4 to H. Set B is a bit instruction, which means 4 to H is bit address. So you can see bit 2 is here, bit 2 is here. Bit 2 is here belong to 2H byte address. So it's location 2HH. CLR also CLR 67H, 67H. You can find the 67 here. 67 here. Yeah, you can find 67 here. 67 here belong to byte to C. 0FH. 0FH. 0F is here. 0F is here. Belong to 1H. Belong to H. So if you can understand you can understand this map. You know the relation. Relation. To avoid confusing regarding the address 0027FH, the 128 bits of RAM have the byte address of 027FH. Can be accessed in byte size. Use various address model. Direct and register in direct. The 16 bytes of RAM location 20 to FH have a bit address. We can use only the single bit instruction, and this instruction use only direct addressing model. Instructions that are used for single bit operation are as following. This table is for single bit instruction. Set B, CLR, CPL, JB. If you see these instructions, you know the address after the instruction is a bit address. The address. Well, all of the SFR registers are byte addressable. Some of them are also bit addressable. You know, the SFR register, some is byte addressable, some are also bit addressable. So you can use it as byte addressable or bit addressable. It's okay. The ports P0 to P3 are bit addressable and byte addressable. We can access either the entire 8 bits or any single bit of I/O ports P0 to P7 to P0 to P3 without altering the rest. If you want to access one bit, you just use the bit instruction. When accessing a port in a single bit manner, we use the syntax set B x point y, sp point y. You use x. X is the byte address. Y is the bit. Y is the bit from 0 to 7. Y is the bit from 0 to 7. So you can use this syntax. For example, set B P1.5 set bit 5 of port 1 high, which means bit 5 of point 1 is equal to 1. Notice that when code such as set B P1.0 is assembled, it becomes set B line 0H, line 0H, which means you use P1.0, but when your program is assembled, the assembler becomes the P10 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 .0 to the address, to the bit address. You can see P1, this is the P1, this is the P1. P10 is line 0H, P1 is line 0H. So it becomes line 0H. This is the address for the P0, P1, P2, P3. If we access, if you want to access the port with the byte address, you just use the first address. Just use the first address. Here, this is P0, P1, P2, this is P3, P3. Yeah, this is P3. You can see P0. Byte address 80, bit address from 80 to 87. P1 byte address line 0, the bit address from line 0 to line 7, line 07. So you know the first bit address is byte address. Yeah. Only register A, B, PSW, IP, IE, ACC, SCON, and TCON are bit addressable, while all I/O ports are bit addressable. In PSW register, 2 bits are set aside for the selection of the register banks. Upon reset, bank 0 is selected. We can select any other banks using the bit addressability of the PSW. RS0 and RS1 is for selecting the register bank. Write a program, save the accumulate in R7 of bank 2. This is the program. Here is select the bank 2. Here is select the bank 2. Here is move A to the R7 in bank 2. When you test this program, you can use different bank, which means you can set B PSW.3, set B PSW.4, or just use the combination of 00, 01, 10, 11. You can check your state of your internal memory. You can check. when you use different you can check the memory. You can check the memory. You know your address of your register. You can see from here. I can give you an example. For example, you just use this program. Stop. Delete. We need A is not 0, so we keep this 9. I keep this 9. Yeah. Save. Build. Yeah. Successfully. Successfully. So debug. You can see the program. Here, move A55H. A55H. You can see here A55H. So next, set B. PSW. Set B. PSW.4. PSW.4. You can see the PSW.4. Check from the PSW.4. Here. We can use you know the address of PSW is D0. PSW is D0. So C, A, B, C. I can run the next. Here. Yeah. Here. This is C0. C0, C1, C2 until here. D0 until here D0. 1, 2, 3, 4, 5, 6, 7. So this is 6. 6. Just D0. Just D0. D0 is here. D0 is here. Move A to R7. You can see. Move A to R7. 5, 5, R7. R7, 5, 5, R7. You can see the R7. Into the memory, you can see the 5, 5 here. 5, 5 here. You can check the address. Check the address. This bank 0, 0 is from here, 0, 0, 1, 0, 0, 7, 0, 1, 7, bank 0, bank 2. You can count from here, 1, 2, 3. This is bank 1, bank 2, bank 3. Bank 3 here. And I mean, you can with access with your testing, testing, and know the status in the memory, because in the programming of microcontroller, understand the memory and address is very, very important. Maybe when you use C language, you didn't know much about the memory or address. But sometimes, if you make your program faster or compact, you need make some program with assembly language, and make your program run faster. Sometimes we need access the memory with just with address in your C language. Here is another program. Well, there are instructions such as JNC and JC to check the carry flag. There no such instruction for overflow back bits. Or we use just use this PSW.2, because OV between two PSW, we use the syntax x.y get the address of OV, and use JB check the OV. JB checks the OV. Here is an example. Well, a program to save the status of bit 1P1.7 on RAM address bit 05. 05. Just move this to C and C to 05. And this. Here, this is example. Is simple, very simple. Right, all this program, I need you to test with Pro Tools. Okay. This is assignment for next week. Next time. This all. Okay. And the test. You know, if you don't do some exercise, you will not know nothing about the microcontroller. Yeah, I told you before, when I learned the microcontroller in the college, after I finished the book, I know nothing. So, when I want to go to the go to the graduation, I get my book back and study by myself. So, yeah. Because when I am in the college, there's no hardware for the exercise. There's no software for the simulation. Just read the book. The bit directive is a widely used directive to assign the bit addressable I/O and RAM location, which means you can use bit address instruction. Make this LED is equal to P1.7, just like the EQU, I introduced before. Can you remember? Yeah, EQU. Just like the EQU.
Oh.
Yeah, EQU for byte address. But not only for address. Some number is okay. Allow a program to assign the I/O or RAM bit at the beginning of the program. Make it easier to modify them. If you use LED bit P1.7, when you want to change the address, you can just change here. Then you can use LED represent your bit. Here is LED. Here is your LED. You can use the LED in your program represent P 1.7, P 1.7. Here is the program. Assume that bit P2.3 is an input and represents the condition of an even. If it goes high, it means that the even oven, it means oven, is hot. Monitor the bit continuously. Whenever it goes high, send the high to low pulse to port P1.5 or turn on a buzzer. Solution oven underline hot, and represents P2.3, buzzer represent P1.5, You can just use two string for your for these two address. Use the EQU to assign address defined by names like P.7 or P2, P.7 or P2. Defined by address like line 7H or line 80H, line 0H. A switch is connected to P 1.7. Write a program, check the status of the switch and make the following decision. If SW is equal to 0, send 0 to P2. If SW to 1, send 1 to P2. Send 1 to P2. Sometimes maybe if you use the program in the PPT, on the PPT, you find some error. You check the reference book. You can, for example, you use EQU. You can find the EQU. So many EQU. I can use here is instruction set. This program is not good for searching. I can use another program. If you use your directive like this, if you found some error, you may be replaced by the bit address, bit. bit address, just like here. Bit, just like here, we use bit. Sometimes, if you use bit is correct, maybe use EQU is not correct. Maybe not correct. The 8052 has another 128 bytes of on-chip RAM, which means 8052 has more RAM than 8051. So if you use 8052, you can use more RAM. It is often call up memory. You can call the memory another 128 byte memory. Use indirect address model which use R0 and R1 register to point with the value of 80H or hell. Just use code like this, to access the high up memory. The same address space assigned to the SFR, and the other part is the same. Here is an example for 8052. You can test this program on your computer. Here is the finish about the addressing model. Address model is important. Mostly we use the address model. Sometimes maybe you found the error. Maybe the address model is there's some error in your address model. Here introduce the arithmetic and logical instruction. Arithmetic, which means you use the add, sub, and divide, multiply. This maybe you think is very simple for you to understand, yeah? But you didn't know for the microcontroller, maybe it's difficult for microcontroller to use the arithmetic, especially when the multiply and divided is difficult for the program with assembly language. But this is fundamental for your program. And a common source. This is instruction format, which means A equal to A plus source. The instruction add is used to add two operand. Destination operand is always enriched A. Destination always enriched A, which means the first is A. First is A. You need to remember. Source operand can be registered immediate dates, or in memory. Memory to memory arithmetic operations are never annulled, which means you cannot make add in the memory. Show how the flag register is affected by the following instruction. This move, this add is add 4, 5 and 0b. Cy is equal to 1 since 0 is carried out from D7. Pf is equal to 1 because the number of ones is 0, no 1. So it's an even number. If the propagation of a carry from no byte to high byte is concerned. So here we use the ADDC. ADDC add with the carrier, which means you can, if you have a carrier before the add, you need to use add C. Sometimes we use BCD as your number. BCD, the binary representation of the digital 0 to 9 is called BCD. Use 4 binary. Represent your digital. We use 8 bits for a value in the microcontroller 8041. But if you use BCD, use 4. Just use 4 for your number. This number is just remember. It's different from the 8 bits, which means we don't consider about the different bits, just represent the digital, I give you an example. If you have a digit 1, if you use 8 bits is 40 and 301. But if you use BCD code, just 30 and 1. If you have a number 11, use BCD is 301. But if you use 8 bits, your bit is just B. So you need the difference between the BCD code and the 8-bit number. 8-bit number. Unpack BCD code. In unpack BCD code, the no 4 bits of the number represent the BCD number, and the rest of the bits are 0. That the bits are 0. This is the BCD code. If you convert to 8-bit number, you can just add 40 before the BCD code. Here is 40 for line 5. Pack BCD code. In pack BCD code, a single byte has 2 BCD number in each. One in the lower bits and one in the up 4 bits. Which means this is for 5 line each. 0101 is 5. 1001 is 9. 1 is 9. So you only remember the unpack and the pack BCD code. Unpack BCD code. Adding 2 BCD numbers must give a BCD result. If you use BCD, you get the BCD result. Get the BCD result. If you want to get the BCD result, you need the directive DA instruction. You need this instruction. DA instruction is provided to correct the mentioned program associated with BCD addition. The DA instruction will add 6 to the lower level or higher level if needed. Normally, if we use DA instruction for a number, this number will convert it to BCD code. And we can see this program. Move this A is equal to 47H, first BCD operand. This is the second BCD operand, 25H. Add A and B. Addition A is to 6CH. DA just for BCD. You know, in BCD code, just there is no ABCD, F, E, F, just 0 to 9, just 0 to 9. Here, in the BCD code, just 0 to 9, no A to F, no A to F. The DA instruction works only on A. In other words, While the source can be an operand of any address model, the destination must be in register A in order for DA to work. DA to work. This is a summary for the DA instruction. After an add or ADDC instruction, if the lower neighbor 4 bits is greater than 9, or if AC is equal to 1, add 0110 to the lower 4 bits. If the upper neighbor is greater than 9, or if CY is equal to 1, add 110 to the up 4 bits. If you want to see the result, you can check on the program per toast, on the software per toast. Here is another example for the add, for the BCD and add. Next, I introduce the subtraction. Subtraction of unsigned number. We use SUBB in the 8041 for subtraction. There in many microprocessor, there are two different instructions for the subtraction. SUB and SUBB. But in the 8041, we only use SUBB. The 8041 use add security to perform the subtraction. This instruction format. SUBB a common source. To make SUB out of SUBB, we have to make CY is equal to 0 prior to the execution of the instruction. SUBB is subtract with borrow. The borrow is on the CY flag. Sub when CY is equal to 0, take the two complement of the subhand source operand added to the manual end, invert the carry. Maybe if I just introduce the code, you feel boring, yeah? You feel boring. So I think you test this program by yourself is better. But it's okay. You test the program by yourself, and then know the status, the status of register. So I give you assignment. You test the program on the software proposed for everyone. For everyone.
This one.
Everyone. I give you the PPT. You don't. You need to take a photo. I give you the PPT. You test every program.
In this PPT.
Yeah. And screen recording for your process.
Oh.
Yeah. If I can see some something about your finding your correcting your error, that's good. Yeah. Maybe there is some error in the program. So you need to find out and correct. Okay.
Yes. Okay.
You need to work hard. Yeah. I give you to